Hi, Science 30. I'm going to finish up this lecture series in electromagnetism. It shouldn't take too long to get through this part of the lecture today. We're going to give you a little introduction to astronomy, space, and gravity. This is actually the Crab Nebula. So this is a star-forming region. There's lots of dust and gas in there, and that's what you see. With multiple stars behind it. So we're going to study astronomy here, and astronomy is the science of objects and phenomena that originate outside Earth's atmosphere. It's going to be a very brief introduction, but you'll get a little gist of it. So when we look at electromagnetic radiation in space, we're primarily knowledgeable about the universe beyond Earth through the study of all this electromagnetic radiation. So studying gamma rays and X-rays and radio waves, and then how those waves are influenced by gravity, which makes gravitational waves. So the sun itself is our closest star. It's fueled by a process called fusion, where hydrogen atoms come together to make helium. Fusion is what we're trying to achieve on Earth. In order to have sustainable energy, you need very, very high temperatures and very dense mediums to do that, and we just can't simulate that on Earth currently. So fusion happens when two smaller nuclei join to form a larger nucleus, and this releases a massive amount of energy. The sun can do this because it's really big, so it has lots of gravitational force, and that makes it hot. So the sun's core is about 15 million degrees Celsius. What happens is two isotopes of hydrogen called deuterium, so it's hydrogen with an extra neutron. They bond to each other and form helium, and the energy gets released as gamma radiation. So you can look at the sun's energy profile here. So again, look at my notes for this. These are prominences coming off the sun due to the sun's magnetic field. Convection happens in the core. Sunspots occur also because of the magnetic field. We get solar winds from the magnetic field. Right? You can see solar flares coming off the surface. So gamma radiation is released as photons. And as they leave the core, they collide with particles outside of it. The sun is mostly hydrogen and helium. As these gamma photons collide with particles on their way out, they lose energy, and the radiation gets converted to lower energy EMR, mostly UV and infrared. So the sun's surface is only about 6,000 degrees Celsius because of that. So the core is really hot. I mean, 6,000 degrees Celsius is still extremely hot, but orders of magnitude smaller than the temperature of the core. Solar flares will emit X-rays and gamma rays. They're created as the sun's magnetic field reorganizes and re-energizes the UV and infrared that make it to the surface. The sun emits radiation from the entire electromagnetic spectrum. Most of that radiation is absorbed by the Earth's atmosphere, and the solar winds from the sun create the aurora borealis, or the northern lights. So I'm going to talk quickly just about properties of light, because this is what we're studying essentially. Like EMR is light. So this is what we study in space to understand what goes on. So just your laws of your laws of reflection and laws of visible light. We know that light travels in straight lines. Light can be reflected, and it reflects at 90-degree angles. Oh, excuse me. Light can bend, and we'll talk about that. And light is a form of energy. So you should understand those four properties. So this is refraction. So this shows, these are sundogs on a really cold day in Alberta. So the light is moving through ice particles in the atmosphere, and that creates, sort of a reverse rainbow. So refraction is the bending of light. Sun is low in the atmosphere in the winter here. This permits more bending of light during the winter season. So that's refraction. Right? So the reason why light bends is because as it moves through denser medium, so this is a crystal, as it moves through denser medium, it slows down, and that changes its trajectory. This is when it bends towards the incoming beam, that's called bending towards the normal. So it bends towards the normal when it slows down, and then as it leaves and enters a less dense medium, it bends away from the normal. So it's kind of this imaginary 90-degree line. Okay, so the bending of light due to its change in speed as it moves through different substances is refraction. The speed of light in a vacuum is 300,000 kilometers per second, but that changes as you go through more dense medium. It slows down. All right, refraction is a big thing that we measure. Light itself moves through gas and dust clouds through the universe, and it is refracted as a result, and we can understand the components of what's inside those gases as a result. Right, so if light hits an object at an angle, it will bend. It slows down as it moves through a dense medium and bends towards the normal. And it speeds up as it moves from a dense medium to a less dense medium and bends away from the normal. Okay, so as white light moves into a dense medium, it will bend and reveal all its colors, and that's what happens in a rainbow. When light moves through water particles in the atmosphere, and as it does that, it reveals all of its colors, and that's how we get rainbows after rainstorms. Okay, so obviously this is a diamond or a prism. So the first telescopes that we had on Earth were refracting telescopes where light was bent into a focal point. Right, so Galileo created a very primitive telescope that observed the craters of the moon, the moons of Jupiter, and the rings of Saturn. We used a combination of convex and concave lenses with that. Right, light was bent in Galileo's refracting telescope. So as a result, it didn't necessarily make a true image. And one of the other big problems with Galileo's telescope was diffraction happened. I'm going to talk about diffraction. So diffraction is the bending of waves as it passes by obstacles or through an opening. So Galileo's telescope had a very small opening, and as a result, seeing objects that were close together was difficult. So light moving through small openings creates diffraction patterns. So diffraction and refraction happened in Galileo's telescope, and that prevented us from being able to see true images of celestial objects. Again, these are on my slides. So this is diffraction. So think about a boat moving under a bridge or through lock. So if a boat moves through, then the waves in front of it get bent, and so they're coming in flat, they'll get bent and become circular. And so the same thing happens with light waves. So what happened as the light moved through the telescope, the light, rather than traveling in these straight lines, was bent into these half-circular objects. And that affected the quality of the images that we've seen. So this is an image of deep space of the Hubble Space Telescope, and these halos around the stars are diffraction patterns, and that keeps us from seeing true images. And we actually see diffraction more and more as we look deeper into the universe, and as we kind of look to the edges of the universe, the diffraction patterns get even more extreme. So this kind of tells us that we might actually be looking, when we're looking through the universe might actually be a cylinder. And as we look to the edges, we see more and more, right, as light comes in, we see diffraction patterns that are more and more extreme. So we see the effect of diffraction when we look to the edge more, and this leads astronomers to believe that the Milky Way galaxy is kind of down here. Now remember, this is an infinitely large, expanding universe. The Milky Way galaxy is down here, and we're actually looking out the cone of a very dense black hole, and our universe exists within a large black hole inside a complex multiverse. So, adjacent to our universe is another dense black hole that we look out of. So we actually think our universe is this cylindrical object because of the diffraction patterns that we see from observing deeper and deeper into the universe and through the edges. Okay, so we don't have refracting telescopes anymore. We use reflecting telescopes. So we don't have the diffraction problem. So the diffraction problem that we see today is entirely from the incoming light, not from the aperture that we're viewing it anyway. Okay, so reflection is a return of a wave from a boundary. It bounces off at right angles. Okay, remember with electromagnetic radiation we have a magnetic field and an electric field, and they oscillate perpendicular to each other to travel in the same direction. So when we look at reflection, we have to look at the magnetic and the electric field. So with polarization, right, electromagnetic radiation can oscillate in more than one direction, and the electric and magnetic field propagate perpendicular to the direction of travel, as I stated. Right, so we have two transverse waves, but the overall direction is this way. Right, so we'll have an electric and magnetic field. The electric and magnetic field travel kind of up and down, up and down, up and down, but the direction is that way. Okay. Right, so in winter and on sunny days, direct and reflected light can travel into your eyes. This is why we have polarized lenses, because what polarized lenses do is they block out one of the, either the magnetic or the electric field in one orientation. Right, so it'll only allow half of the EMR to come in, because you'll block out one of them in a certain plane. Okay. So that's why it's good in the winter and in the summer, but particularly in the winter, to have, driving sunglasses. Right, so this shows the polarization effect. Without polarized lenses, you get that extra glare. And then with polarized lenses, right, you can block out half of the waves, because one part of the wave is traveling in a perpendicular orientation. Okay, so polarized lenses are important for that as a result. So when we look at reflection, this is from junior high science, but the laws of reflection tell us that when we have an incoming light ray and it bounces off a reflective surface, it will bounce off at right angles. So you have an incoming ray, an incident ray, and a reflected ray, and the angle of incidence will equal the angle of reflection, and this is called the normal as well, just like you have in refraction. Okay, so the angle of the normal, right, it's the angle of the normal will be 90 degrees to the reflecting surface. The incoming angle will equal the outgoing angle. So when a ray hits a mirror, it bounces off the mirror at exactly the same angle. The line perpendicular to the point of reflection is called the normal. Okay, so the angle between incident ray and the normal is the angle of incidence, and the angle between the reflected ray and the normal is the angle of reflection, and those should be equal. So this is what reflecting telescopes do, and so our biggest telescopes today are reflecting telescopes. So what we'll do is we'll collect a large amount of light from space, and then we'll have a concave mirror which collects all that light, and then it will bounce the light off at right angles to a focal point, and then so this won't be flat, but it'll concentrate all of the light rays into one area because the angles will all coincide. That'll hit a secondary mirror, and then we'll hit a focus or observation, and this is usually tied to a computer system today. All right, so they'll all bounce off at the same angle, so all of those light rays will be in the same orientation. So we don't have to worry about diffraction and refraction like you would with a more primitive telescope. The only diffraction and refraction that are happening is from the actual light entering itself. It's not the aperture that's causing that. So with reflecting telescopes is a large circular mirror that curves inward. So there's two big advantages of reflecting telescopes over refracting telescopes. Lenses can have the same effect as a prism, right? So mirrors don't have the problem of refraction, whereas refracting telescopes obviously do. Reflecting telescopes can be made with really large openings because the curved mirror is supported underneath, and it can reflect light to a focal point, and this solves the problem of diffraction. from the actual aperture itself. So this is a really large, so this is what our big telescopes look like today. This is a big modern reflecting telescope in Hawaii, on Mauna Loa. This is actually a mirror of Mercury, right? So Mercury is a liquid metal, so we will collect light from space. It'll bounce off the liquid mercury because we can change the orientation of that liquid metal based on what we're looking at. And then it all goes to this focal point here and to a computer system. And you can see how big that telescope is. Look, there's a person right there. Okay, so reflecting telescopes are by far more useful than refracting telescopes. We can also collect electromagnetic radiation, right? We don't just need to collect visible light, but remember, radio waves are really, really big. And if they're coming from space, they could be kilometers long, right? So we can collect radio waves and long wave radiation from arrays of satellite dishes, okay? So in reality, astronomy is done studying the nature of EMR entering our atmosphere from space. Different wavelengths reveal different information about the universe. And the further back we look, so the deeper we look into space, the longer that EMR has been around, right? So it has lost energy, so the energy is converted to lower energy wavelengths. So when we're studying really, really deep space, we're usually generally studying radio waves and gravitational waves and microwaves. And so we need really, really large arrays to be able to collect that. So radio waves have been very instrumental in us understanding things like the origin of the universe, cosmic expansion, and such things. So we need different arrays to be able to study different wavelengths. So we can study the energy content, wavelength, frequency, and degree of polarization. We can also study the speed of all electromagnetic radiation in the electromagnetic spectrum. We know that they all travel at the speed of light unless they're moving through a different density, unless they're not moving through a vacuum, right? Then they'll slow down. But wave properties dominate at the lower end of the spectrum, and then photon properties dominate at the higher end of the spectrum because the frequency is really, really high. So they act more like particles. So this is a gamma telescope. This is looking into the Milky Way galaxy, and this is showing us where gamma rays are coming from in the Milky Way galaxy. So there's something very energetic at the center of the Milky Way galaxy. We believe it's a very large black hole. The dense gravitational strength is creating very high energy radiation. So there's some very large collapsed star down there, which emits, which is absorbing and emitting light. So how do we analyze starlight? Well, we can study the components of stars, right? The gamma rays and the X-rays and the infrared rays and all that to understand property natures. But we can also study visible light. So the way we analyze starlight, right? We can use a diffraction grating, so a lens that will separate the light into its component parts. So anything that is dense material heated to about 6,000 degrees Celsius will produce a continuous spectrum. No distinct lines over the emission spectrum are shown, and we have unbroken bands of wavelengths. So we can heat up materials to 6,000 degrees Celsius or higher on Earth, and then we can observe which wavelengths of light they emit. They will all emit their own light. And so we can get kind of a light fingerprint of all the different objects on the periodic table. So we've been able to do this in the lab, and so as a result we have a light fingerprint for all of the molecules on the periodic table, so all the elements. So when we observe starlight, we can then, right, we will absorb, right, so when we observe starlight, we can take that light through a diffraction grating, reveal what wavelengths are present, and that will let us know what types of ions are actually in that light, so we know the components. So we know what stars are made of as a result. Okay, So we can look at, this is called spectral analysis. So we're looking at emission spectrums and absorption spectrums. So I'm going to talk about what these are. So when we look at absorption spectrums, it's a dark line spectrum. So you'll have a continuous spectrum of light when you observe this. And then what happens is that continuous spectrum, there'll be dark lines that show up, and that shows what wavelengths of light have been absorbed. So when we, so atoms of a particular element in a low pressure gas will only observe certain wavelengths, and this allows astronomers to determine the components of celestial objects. So we can look at absorption spectrums and we can look at emission spectrums. So with emission spectrums, we're looking at what rays of light are being emitted and what isn't. So the emission lines will be the same as absorption lines if we're looking at the same element. The difference is emission spectrums are coming from hot objects. So they are things that are producing their own light, but if they only have certain elements, they're only going to produce light at certain wavelengths. Okay, absorption spectrums generally are observed with cool objects. So the cool objects will absorb wavelengths and leave gaps. Okay, so with emission spectrums, the gas is heated up and emits light. And the reverse happens for the absorption spectrum. The wavelengths that the gas absorbs are emitted when brought to a higher energy level. So only certain wavelengths are emitted rather than certain lengths being absorbed. So we can use a mass spectrometer to observe what wavelengths of light are absorbed, and as a result we can see what elements exist in either hot objects that are producing their own light, so we'll observe that through emission spectrum. We can also observe cool objects in the universe, like a cooling gas, and that gas will absorb elements of certain wavelengths, and so you'll see those lines as gaps in the continuous spectrum when we use spectral analysis. Okay, so we observe the chemical composition of clouds of gas around stars, star-forming regions, and around planets. This tells us how stars, galaxies, and solar systems form, and also tells us how these large objects move. So this is the emission spectrum for hydrogen. So when there's a really hot object producing hydrogen, we will see, or emitting hydrogen, we will see these lines. Now, if hydrogen, as ionized radiation moves through like a cooling gas or cooling cloud of gas, you'll see the gas absorb light at these wavelengths. So when we observe the gas itself, you'll see gaps in their spectrum that way. Okay, so this is a hot object, this is a cool object. So here are emission lines for different elements. You can put multiple spectrums together to determine the contents of stars. Hydrogen, helium, lithium, oxygen, carbon, nitrogen, neon. So you can see these different things. If we were in class, you'd be doing a lab on this, but we're not in class, so unfortunately, I can't throw up the emission tubes that I have, unfortunately. So that's how we observe what's in stars. We also observe what's going on in the universe by looking at how things move. So so these are two links on YouTube that you can observe for the Doppler effect. So we look at Doppler shifts. So the Doppler effect is a change in the observed frequency of a wave due to the relative motion between the source and the observer. So we generally observe the Doppler effect in relation to sound, but it has really large implications for astronomy, right? I mean, light travels as a wave, as does sound. There are different types of waves, right? Sound is a pressure wave and light is an energy wave. But here's the deal, is due to relative motion, objects observed in the universe that are moving toward us are seen as higher energy. They're seen as blue shifted, right? Roy G. Biv, so blue's higher on the spectrum. The EMR receive appears to be higher frequency. It's not actually, it's just a perception. And objects rapidly moving away from us are seen as redshifted. Okay, so almost all objects are rapidly moving away from us, and that's why we receive redshifted light, because the universe is expanding. So, I turn on the sound here.
Effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense. But it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you. And a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so Doppler effect is a change in the observed frequency of a wave due to the relative motion between the source and the observer. So to the source, there's no change in frequency, but to the observer, depending on where that individual is, you'll either observe a wave as higher frequency or lower frequency. And that's what we see with light. Objects that move towards us are blue shifted because their waves are bunched up and appear to be higher energy. Objects that are moving away from us in the universe, their light waves are further apart and appear as lower frequency. And that's how we know that the universe is expanding. So that's the Doppler effect. Right, so blue shift and red shifted light. So the last piece of this unit is looking at star classification. Now, this is a very simplified version of how stars form and what goes on with stars, but it suffices for what we're learning in Science 30. So we have low mass stars, intermediate mass stars, and high mass stars. So you need to be able to classify stars. So if we look at low mass stars, so there's a whole piece of stellar astronomy looking at where stars are on a sequence on a sequence chart. It's called the main sequence, and stars either exist along the trajectory of the main sequence or anomalous to that. But anyway, low mass stars, they always start as swirling dust and gas called protostars. Low mass stars, they live their life as a main sequence star for most of the time. When they start to lose their fuel, they puff up, turn into red giants. They'll blow off extra hydrogen with helium left over, puff up again, and what happens is there's an isostatic rebound. So this helium, this initial hydrogen sloughs off, you're left with helium. This helium expands as it's spent, and then collapses in on itself, and then rebounds outward as a nebula. So this is a dead star. This gas and dust will then make new stars. So as a star dies, its remnants will be recycled, and then a low mass star will end up as a white dwarf, very dense helium core object. Intermediate and high mass stars, they burn a little bit hotter, so they'll be blue main sequence stars, right? So they have light that is shown with a higher frequency. Right, these guys become supergiants, and they'll have this isostatic rebound on a bigger scale again, right? So the core sloughs off, gravity will bring it back in, and then it blows up, right? So this expanding core will move inward really, really fast, and then blow out, called a supernova. So supernova will turn into a neutron star or a black hole. Okay, and a black hole is an area of matter that is so dense that light itself cannot escape, right? So you have very, very high gravitational fields. It may lead to other parts of the universe or other universes, right? We call that wormholing. So there's lots of mysterious physics around these things. So the sun, if you didn't know, the sun is actually a low mass star. That's kind of good for us. So anything that's less than 1.4 times the mass of the sun or the mass of the sun is a low mass star, so any star. So the core will be up to 10 million degrees Celsius. So these stars are big, but they're not that big. So gravitational forces cause gas and dust to collect, turning into low mass stars. Fusion happens, right? So fusion is the main fuel that causes stars to work. So once fusion has converted hydrogen to helium, the core collapses, the outer portion expands, and we have a red giant created. Core temperature rises, and the outer layers are puffed out as the star destabilizes. And what's left over will be a dense white dwarf. So because there's less mass, the fuel is burned slowly. So it's a more efficient star. It's kind of like a Honda Civic versus driving a Ferrari. So low mass stars have a longer lifespan than intermediate and high mass stars. So the sun will live about 9 billion years.